Thank you so much, Jem, for the great introduction. I'm Ajit. I'm the co-founder and CEO of TurboML. Really excited to be here. Today, I want to talk about TurboML's platform and how we're able to leverage fresh data for ML. So let's get started. Uh, So first, let's define what fresh data means. So there are multiple different definitions for data freshness out there. The way I'll define it is, it's the delay between when your data is created and when it can be used in your application. So then actually, fresh data for machine learning would mean how do you make your data with a given freshness accessible to your machine learning system. For example, here could be I'm able to use the user's latest transactions and behavioral data to detect fraud. Now, the way most teams use fresh data for machine learning is via features. So you can use your fresh data to update features. You can define on-demand or aggregation-based features, and then depending on the logic and the freshness level that is required, you can decide on a mode of compute. So whether it is on-demand or asynchronously using a streaming-based computation. So an example here would be that I define a feature like an average transaction amount for a given user in the last 30 minutes or something like that. Now, is that all you can do with fresh data? Absolutely not. Even though most teams currently use fresh data for features, and it can provide very good context about the real world to the models themselves can still be outdated. So just for context, the best teams who are using fresh data for features, their feature freshness is in the order of a couple of seconds or a minute. However, their model freshness is somewhere in a few weeks or even months, which is very outdated. Now let's motivate why or where you might need a fresher model. So one use case that we're working with a financial institution is around fraud detection. And here what we're seeing is so labels and new information is very scarce, especially for somewhat newer evolving fraud patterns like money mules. So in these scenarios, what you need is to be able to incorporate learnings from this very little data and use that to detect and prevent similar frauds as soon as possible. So the only way you can do this is by improving your model freshness. Another use case is recommendations. So this is different from the fraud detection use case. Here, the challenge is that the setting itself is very non-stationary and highly dynamic. So even though real-time features can help you capture local context about what a particular user is looking at or what they're browsing, what they might like, you still need to capture global trends. So a particular segment, what are they interested in? Again, the solution here is by improving model freshness. So if we summarize this, fresh data for machine learning beyond features can be in multiple different ways. Machine learning itself is highly data driven, and you can use the fresh data to update ML models in different scenarios. You can improve deployments. So most ML deployments are not a one-off process. You have model selection, model calibration, drift, data quality, all those other processes which require fresh data to continuously improve. And you can also experiment and iterate faster. Now let's look at how you can actually implement something like this. So since we talk about model freshness, let's see how you can improve model freshness. Suppose I'm targeting a model freshness for one day, right? And suppose that I want to train my models on the last 6 months of data. Now, a naive approach for this would be I have daily retraining job. However, there are a couple of limitations. The first one is if I have independent training job, I might modify the code at some point, and the whole process is likely to be bug prone. The second thing is it can be very resource intensive. In fact, if it takes longer to train my models than my targeted freshness, then it won't even work. So for example, if I'm targeting 1 hour of freshness, but my model training takes 2 hours, then it won't even work. So how can we solve this? We can actually draw parallels between what we already know, which is feature computation, and model retraining. So let's consider the following feature: average transaction amount for a given user over the last 24 hours. And this feature needs to be updated or computed every hour. Now, the same approach that most companies or most people here would take, compute this feature, will also work for model training. Let's see how. So the way typically you would do this is, for the first time, you will fetch all transactions in the last 24 hours and aggregate them. Now, after 1 hour, when you have to actually update it, You won't do it in a stateless manner where you recompute all these things from scratch, but you will do it in a stateful incremental approach, where basically you are able to update this value only on the changes in the last 24-hour window. This is exactly what we'll do even for model training. So a stateless approach for model training would be that I have my data, I'm an algorithm, I use that to train a model from scratch. However, a stateful incremental approach would be I have my algorithm, I have some new data and a model state. I'm using this to make an incremental update on a model state and get updated model state. So for example, if I have a model from yesterday and I have data from yesterday to till now, I can use that to update my model to get a model for today. Taking an example of neural networks, here the state would be the model weight, any pre-process that you might have, and the optimizer state. So if you're having a learning rate schedule, those things will come into place. Now, you can probably imagine that a stateful incremental update here would just be a couple of gain distance steps. But here we can see the issue. So basically, unlike feature aggregations, here the batch size and even the order in which you make computations matter. So for example, let's say I can have 100 online steps, or I can have one step with a batch size of 100, and they'll have very different results. So incremental learning is a separate, domain of its own. There are a lot of libraries which can help you, get used to incremental learning algorithms. So River is one of the most popular libraries. Warpal Rabbit from Microsoft is also a great alternative. And Avalanche also deals with continual learning or incremental learning for neural nets. Now, we have a way to update a model, right, incrementally. How do I prepare the training data for that? So here, what you can use is a technique called log and weight. So most likely, when you are making predictions for a given data point, you're already computing the features for that. You can store these features, and then later, when you actually get the label, corresponding label for this particular data point, you can use that to join with those features, and then pass this to your training bucket or training topic, or however you want to use this for training. The limitation here would be that this does not work for historical data, where if you are introducing a new feature, you might require backfilling. So we talked about model freshness, but as we discussed, MU model itself is just one part where fresh data can help. There's also model deployment. So typically when we deploy a model, we have processes like model calibration, performance estimation, model selection, data quality and drift, testing observability, all those different processes. All these depend on data, and all these can be continuously improved using fresh data. Just to take an example, let's say I have a contextual bandit-based model selection setup. Here, whenever I get a new label, I can use that not only to update the model, but also figure out what metrics or rewards I want to compute to pass to my bandit and help it choose the most relevant model. So with all that in place, let's look at TurboML at a glance. So with TurboML, you can define different components like data sources. You can define features. This can be defined either using SQL or a higher level data frame API with Python, UDFs, and UDAs. You can define models. So because these are incremental models which support incremental learning, you can choose from out-of-the-box algorithms for incremental learning, or you can write your own code in Python. You can select metrics, you can select analytics, you can select model deployment configurations like calibration, etc. And you can declare all these different components. The next part is how will these components update? So you can define or choose a method in which you want to update these particular components. For example, the data source can be updated either via pull-based ingestion, where basically I'm pulling it via some connectors from some other source, or I'm pushing events to it via some kind of SDKs, right? Features can be updated. I think this we already know. They can be updated in a streaming manner or in a batch manner, right? Model update is, I think, the new part for most people. So here you can have online training, which means you are able to update the model on every new data point, or you can have trigger-based updates. So for example, let's say if the performance drops below a certain metric, or let's say if you observe drift in some key features, then you trigger an update. Or you can also have ad hoc updates. So I think we were discussing about GDPR, right? So let's say if I want to remove a particular data point from my model training, so I can choose the checkpoint that was basically just before that particular point. I can pass in ad hoc data, so basically the data from that point, without this particular example, and then update my model. So basically, I can pass ad hoc batches of data to update my models. And obviously, I can also choose how I want my metrics and model deployment process to update, again, streaming versus ad hoc updates. The tech stack that we use with TurboML is shown on the slide. So basically, for real-time data, we're using Apache Kafka as the main protocol. For historical data, we're using Apache Iceberg. For all the stream processing that we're doing, we are using a combination of Apache Flink and Rising Wave, depending on what kind of computation it is. To enable a higher level data frame API, we're using IBIS. And the advantage here is we also get for free all the backends that IBIS supports or will support in the future. For batch computation and retrieval, we're using a combination of Data Fusion and DuckDB, again, depending on what kind of computation it is. Now, in most scenarios, right, like when you're sending ad hoc batches of data, there's a lot of data transfer that is involved. So for that, everywhere in TurboML, we're using Apache Arrowfly as the main protocol to share data. Metadata is stored in PostgreSQL. We are using an S3 or min compatible object storage for storing our model version. So this includes both periodic checkpoints as well as any named or stored versions. To implement our login weight, we are using RocksDB as the main KB store. And all our analytics, so basically all the metrics that you saw, all the model selection or other basically analytics that we're doing, all of that is happening on Stardogs, which again uses Kafka and Iceberg as the main sources. Now, obviously, when you're building a new system like this, which is following a different paradigm, so streaming first instead of batch, there can be multiple different challenges. Here, I've listed a few challenges that we've solved at TurboML. The first one is around data. So, because it's all non-session data throughout, it makes even traditional challenges like data quality more pronounced. The second challenge is around the algorithms itself. So, if you're using incremental learning, you can have different modes of failures, like catastrophic forgetting, where basically you forget old data that you've learned on, or basically you want to make sure that your models are robust and stable enough to be used in your end applications. MLOps itself is considered pretty tough for even a static batch setting where your models are not changing, but it is much tougher when you have a continuous streaming setting where you have a lineage of different model versions. Inference scaling is obviously a challenge for any platform. But here, since the main idea is that you want to make it more efficient than batch retrainings, so you have to be able to do this in a cost-effective manner. And finally, if you're building any platform, there's always a people challenge involved. So basically, whatever you're building, is that intuitive enough for people to actually use or build their use cases over? Yeah. I can see that my time is close to an end, so I'll stop here and take any questions.